first research seminar of this spring semester. I hope you all had a nice vacations with a lot of traveling, skiing, and so on. So our first lecturer in this spring semester is Francesca Scarabel from York University in Canada. So this is also the reason that we have a seminar of this at this a little bit, at least for us, a little bit unusual hour. And Francesca will talk about renewal equation model for disease transmission dynamics with contact tracing. So a very actual talk for this time. So
thank you very much for the invitation. Thank you for accommodating the time difference. I'm really happy to talk here today. As I was saying, I actually come from Northeast Italy, so quite close to you. And so I'm going to talk about work that I've been doing here in Toronto, motivated by the recent pandemic of COVID-19, but actually the model is quite general. And it has some interesting mathematical aspects, not just epidemiological aspects. The work has been done with my current supervisor, Jianan Wu, and Lorenzo Pellis from the University of Manchester, and Nicholas Ogden, who's from Public Health Agency of Canada. And it is available on medRxiv. A preprint is available on medRxiv if someone is interested. And as I was saying, the idea is to model contact tracing. So as we probably have all heard, as it was a very important topic in especially the first part of the COVID pandemic before vaccination now is coming in. Contact tracing is the process of identifying and isolating individuals among the contacts of one confirmed infected cases. So once one case is infected and detected, then public health officials try to find the contacts or infections between the contacts of this case. And the advantage of contact tracing is that it allows to stop as many infection chains as possible and as early as possible if it's done efficiently. And there are different strategies that differs in how or what contacts are searched for. Forward tracing denotes the process of searching for secondary infections of a case, so the secondary cases, whereas backward tracing aims at searching for the infector, like who infected this one person we have found. Whereas full tracing combines both strategies. So we search both for the infector and also for all the secondary cases that has followed. So why modeling contact tracing is hard? The reason is that a model should account for different aspects. We should describe the infection spread, as in all epidemiological model. Then we should account for another diagnosis program or screening program that initiate contact tracing, so through which we can find the first initial infected case and then start contact tracing. And then we should keep track of all the contacts between individuals and the infection transmission. And now the problem is that contacts of an individual that is detected now are distributed in the past, and they have already progressed through different disease stages possibly, and possibly have generated new infections. So it is quite hard to keep track of this aspect. And most studies, because of this, most studies use stochastic models, in particular stochastic agent-based models, but also branching processes or network models, and then mean field approximation. But the idea of stochastic age in the base model is indeed that every single individual in the population is stored and somehow follow computationally, and we can describe each single individual at each moment in time in the population. So those involve huge computations to be solved and simulated. The more used compartmental ODE models fail to capture the details of the context distribution over time. So they can roughly model contact tracing, but it's very difficult with compartmental ODE models to precisely capture the idea that contacts happened in the past, and we don't know yet how much time has passed, and if they're infectious or not, and whatever. So here in this talk, I want to focus on the modeling approach that we took. And the modeling approach is fully deterministic, but then it goes from the individual level to the population level. So the idea is really to first prescribe parameters for each individual in the population, which are anyway assumed to be identical to each other, but they are characterized by one set of parameters, and then calculate from the individual level, calculate what happens to the population level. And then I will also show some examples of application with parameters coming from COVID-19 to investigate the contribution of diagnosis. And diagnosis, I mean diagnosis from symptoms, and contact tracing to control the infection. And please stop me anytime. I'm happy to answer questions during the talk. Now, the model is an SIR type model. So in standard SIR type models, the population is divided into three classes. The individuals who are susceptible, so they have no immunity to the disease and they can contract the infection. Individuals that are already infected and can infect others. And removed individuals who have been infected, but now they have recovered or they have been isolated. But the idea is that they are not infectious anymore and they are permanently immune, so they cannot get infected again. And then, because we are in a deterministic setting, I will assume that individuals are identical to each other. And then mixing is homogeneous in the sense that every individual can have contact with any other individual in the population with the same probability. And I will consider three main processes. One is infection. The second is diagnosis from symptoms. So the idea that every individual, infected individual, can develop symptoms, then go to a clinic, get a test, and be diagnosed. And then the third process is indeed contact tracing. So I will try to describe each of these processes singularly. But before I go to the single processes, I want to talk about this idea of individual at the individual level parameters. The idea is that we prescribe every parameter or every individual property in terms of the time since the infection or age since infection. So given one infected individual, we have a quantity that describes how much time has passed since infection. This is tau. And all properties of the individual are characterized by tau. So we can prescribe the infectivity, beta, in terms of the age since infection, the incubation period, which is the time before symptoms, the symptom onset, and the diagnosis rate, which is related to the probability of this individual being diagnosed at a certain time, or the tracing rate, which is related to the probability of being traced at a certain time. So these are all prescribed in terms of the age since infection. And when I say age in the following of the talk, I always mean age since infection. So infection age, there's no no demographic age in the model. So the first process is the infection process. And the idea is that infection happens upon contact from a susceptible individual, which is in the class S, with an infected individual in the class I. And every infectious individual or infected individual has a certain infectiousness profile that depends on the time since infection. And this accounts both for the number of contacts that this individual has and the probability of transmission. So if we want to calculate the number of new infections that one individual with age since infection tau generates, we need to calculate how many. So we need to take the infectiousness beta, which accounts for how many contacts and the probability that there is transmission of the virus or the infection. And then only those contacts that are actually susceptible will be infected. So this fraction here describes the proportion of contacts that are actually susceptible. And N0 describes the total population size, which is assumed to be constant. So this describes the number of new infections from one single individual. Then if we want to compute the total number of infections at a certain time, so this is related to the number of new cases that every day we hear from the television, then if we assume that individuals are never isolated, we just sum up all the contributions. So the idea is that we know how many new infections are generated by one individual, and then we count how many individuals that are infected with age tau are in the population. And here, this is given by this term, y at time t minus tau, where y is indeed describing the number of new individuals, new infections at time t minus tau. And if these individuals have never been isolated, they are still infectious, going around in the population. I ignored the possible disease-induced death here, and somehow I assume that if they are not infectious anymore, that can happen. This is described by beta. I assume that beta is 0 when these individuals are not susceptible and infectious anymore. But then when I integrate over all the possible infection ages, I get the total number of new infections, and this is given by y. So this integral equation describes the evolution of the incidence, which is the new number of infections at time t in the population. Now, we want to add the two more processes, the process of diagnosis and then the process of contact tracing. Regarding the diagnosis process, we assume that this is completely known because it is determined by epidemiological parameters. So for example, what is the incubation time, so the time to symptom onset of the disease, and what is the test positivity. So for example, when does a test turn out to be positive? And also this is fixed by the screening policy. So are we testing symptomatic individuals only, or are we testing randomly, or are we testing everyone in the population regularly? But once these characteristics are fixed, we assume the diagnosis process is given. So we can just prescribe parameters for it. And the parameters we prescribe are the rate, the individual rate at which one individual is diagnosed in terms of the time since infection. And if this is a rate, this means that when we multiply this rate times the differential infinitesimal element dt, we get a probability that an individual is diagnosed in a small interval of time. Then from the rate, we can also define the probability that an individual has not been diagnosed. This is also called survival probability. And this I denote by calligraphic F with the subscript D always. And this is defined by the negative exponential of the integral of the rate. So yeah, again, this denotes the probability that an individual has not been diagnosed before a certain age since infection. And regarding the diagnosis process, we assume that this is independent of time. So it never changes in time. And we assume that after diagnosis, individuals are perfectly isolated. So they are somehow they don't contribute to the infection anymore. And for the contact tracing process, this is slightly different from the diagnosis process because we cannot prescribe it a priori because it can be time dependent. So the contact tracing depends on how many infectious individuals are in the population and how they interact with each other. So we cannot assume it known. So we take it as unknown, and this will be the unknown variable of the model. But otherwise, we have similar quantities as for the diagnosis. So this H with subscript C will denote, similarly as before, will denote the rate at which one single individual is traced. And note that because this is unknown and in principle it is time dependent, I have also included the dependence on time, not just on time since infection. But then apart from this difference, then from the rate, we can still define the probability that an individual is traced in a certain small interval of time. This is the rate times dt. And then we can prescribe the probability that an individual has not been traced up to a certain time since infection. And this is again given by a negative exponential of the integral of the rate. But this time the integral is performed through the, let's say, the characteristic line. So we integrate along time and time since infection at the same speed. So we again have these three elements which are very similar to the diagnosis process: the rate, the probability, and the survival probability. But this time they are unknown. So this rate here is unknown. And here I restrict to forward contact tracing. Again, this means that once one case is infected, contact tracing searches for the secondary infection. So who has been infected by this one person. And then I assume, again, for simplicity, that isolation is perfect after tracing. So individuals do not infect further. And then for simplicity, I also assume that there is no tracing delay. So when I detect a case, instantaneously, the contacts are found and isolated. And also I assume iterative tracing. This means that not only the contacts are found, but because they are found, also their contacts are searched and found. So iteratively, we search for contacts of contacts of contacts. So, and but not all contacts may be found. We assume that only one fraction, which is denoted by epsilon with subscript C, only this fraction is found, and the other fraction, 1 minus epsilon, escapes tracing. So they are not isolated. Now, here is a little scheme to try to visualize what I've just said. So imagine we have an initial infected case in gray, this individual number 1, and we go forward with time. So this individual going forward means that its age since infection becomes larger and larger. Then during the infective time, this individual can produce 2 new infections, these green individuals, 2 and 3. And they can go on infecting others. So for example, individual 3 infects individuals 4 and 5. And they all proceed with the with time. Now, the idea is that if this initially infected case for some reason is diagnosed because it has developed symptoms and it tested positive, then instantaneously after this individual is found, all its contact or some part of its contact are traced. So if they are traced and found, they are immediately isolated and they don't produce any infection anymore. And also, because we have assumed iterative tracing, also their own contacts are traced. So also 4 and 5. But now we said that not all contacts are traced. Some can escape with some probability. So in this example, individual 5 escapes tracing. We don't find it for some reason. Then this 5th individual will go on producing new infections until it is possibly diagnosed again. So that is just to give an idea of the instantaneous tracing. So now I go a bit into the details of the model, and I may sometimes skip some details. I hope you can trust the model anyway, and I'm very happy to go back a bit slowly later if someone is interested. But I will first start with again with the infection process. So again, with describing the incidence, so the number of new cases at time t. Now we had an equation in absence of isolation, but now if we put diagnosis and contact tracing in the model, this also changes the number of new infections every time. So the idea is that we had this equation beforehand, but now we need to include another term here that describes the probability that an individual has actually not been isolated yet. So this individual represented by that was infected at time t minus tau is infectious and can generate new infection only if it was not isolated. And this calligraphic F, so it represents the probability that an individual has not been isolated. And this means that has not been diagnosed and has not been traced yet. And because individuals are independent of each other, and also diagnosis and tracing of an individual are independent processes. So this survival probability is simply given by the product of the two survival probabilities. And of these, the first one is assumed to be a parameter of the model, but the second one is unknown in the model. And just to repeat, this is a renewal equation in Y for the incidence Y. And still, I haven't said what happens to the susceptibles, but this is simple because susceptibles change in this model. Susceptible change only because they become infected. So we can prescribe an ordinary differential equation for the susceptible so that the derivative equals to minus the incidence. And then when we prescribe the initial condition, we can solve explicitly this equation and get and express the susceptibles as only in terms of the incidence and of the initial number of susceptibles of individual in the population. So I will write S, but in fact S is completely described by the incidence itself. So as I said, this equation is closed except for the survival probability that depends on the contact tracing, which is unknown. So we need to prescribe an equation for the contact tracing. And the main idea, so the main intuitive idea is that the probability that an individual is traced at time t is proportional to the probability that its infector is detected at time t. And contact tracing is initiated. And an infector is detected in two ways. Either it is diagnosed or it is traced. So this is the So the very intuitive idea, because then formulas will become a bit more complex and involved, but the essential idea is that we can link the probability that an individual is traced at time t with the probability that the infector is traced at time t. This will give us an equation for the tracing probability. And because we have said that all parameters are prescribed in terms of the age since infection, to find the correct equation, we just break down this term by conditioning on what was the infector's age since infection at the time of infection. So this is a little scheme that I will use to then generate the equation. The idea is that we look at an index case, the orange one, and we want to find the probability that this individual is traced at a certain time t, knowing that it has age since infection tau. So having age since infection tau means that the infection happened at time t minus tau. And then the idea is that to understand this probability of tracing, we look at the infector, and we look at the probability that the infector is traced or diagnosed. And we will condition on, okay, what was the age of the infector at the infection time? So first of all, we need to understand what is the probability that the infector had a certain age at a certain time. And that's the first step that I'm going to do here. I'll call psi times ds the probability that given an infection at time t, the infector had a certain specific age in S, in this small interval. And this probability equals the fraction between the number of infections coming from individuals of age since infection in S or SPDS plus DS, so this small interval, over the total number of infections at the time t. And this is simply obtained by, similarly as how we obtain the renewal equation for the incidence, we count, the numerator contains the number of infections indeed that come only from individuals that have age since infection S. And then the denominator sums up all possible ages and all possible infections. So this quantity can be expressed in terms of the incidence and the survival probability. Now I will use this to obtain the final equation for the contact tracing rate. Now, so HC denotes the individual tracing rate, and when we multiply times dt, this means the probability that an individual is traced, given that it has a certain age since infection, so it was infected at time t minus tau. And okay, this is traced only if only a fraction of the individual are traced, this fraction epsilon c, times the probability that the infector was detected at time t. This is what I just said before. We look at the infector, and now we condition on the age since infection of the infector. So for each possible age S of the infector at time t, we calculate the probability that the infector was detected at time t. Okay, so this first term is what we have just computed before. This is the term psi at time t minus tau, which is the time of the infection, and the age of the infector is S. And then the second term here, which is a bit more complicated, but in essence, so sorry if I'm going a bit fast here, but I'm happy to go back here later if someone is interested. But it contains the probability that an infector has not yet been isolated before time t, and the probability that it has been isolated, like diagnosed or traced exactly at time t. This is the sum of the rates here. And then the denominator comes from the fact that we know this individual was not isolated at the time of infection. So the idea is that we can relate the rate at a certain time t with the rate h with subscript c at a different time. And then this slide sums up the whole model. So so even maybe if you for some reason didn't follow until here, maybe we can focus on this slide. The idea is that the model, when we put together the equation, we get two integral equations that fully describes the dynamics of the epidemic. So the second one here is a renewal equation for the incidence, so the number of new cases at each time t. And the first one is an integral equation for that describes the contact tracing process. And this system is closed because all parameters are prescribed, but and we can prescribe the survival probability calligraphic F in terms of the rate H with subscript C, which is the variable of the model, and we can describe the number of susceptibles in terms of the incidence. And an interesting aspect is that this equation is delayed in time. So we can find delayed term in the incidence term here, for example, or here, but it is advanced in the time since infection, and this can be observed here, for example, or in this rate here. And the idea is essentially that when you think of time since infection, the index case is always younger than its infector. That's why we get advanced arguments. And this system is just a system of two integral equations, so it can be solved using numerical methods, for example, quadrature rules. Now, I'm going a bit more in practice. So the model is described in terms of the rate, which is difficult to measure in practice. So one may think that it's quite useless in practice, but actually we have all the ingredients to compute concrete quantities that can be measured in practice if we have data, like the number of individuals that are diagnosed at each time can be computed easily using simply the diagnosis rate, and then the number of individuals that are traced at each time can be computed also. So if we had data describing this, if positive individuals have been diagnosed from symptoms or have been traced, we could compare the model with the data. And then another advantage of the model is that there are explicit formulas for the reproduction numbers. So as probably we have, so we hear a lot in the news about these reproduction numbers. This is a reproduction number is the average number of secondary infections produced by one typical infected individual in a susceptible population. So it describes how infectious a disease is. And here we have three types of the reproduction numbers. The reproduction number describing the very at the very beginning of the epidemic, when the epidemic is unconstrained, or the reproduction numbers when there are diagnoses or contact tracing in place. And there are explicit formulas from the model. Explicit formulas means that the calculations are easier and we can get general insights. For example, it is easy to show in general that an epidemic can be brought under control if the fraction of transmission that occur before isolation is less than 1/R0. So we can somehow quantify the diagnosis and tracing efforts needed to control the epidemic. And I want to conclude with some example of investigation we have performed. They are mostly qualitative because it is hard to obtain data about contact tracing, but they have been obtained with parameters related to COVID-19. And we investigated the impact of diagnosis coverage. So how many individuals are actually symptomatic and can be diagnosed, and the delay for diagnosis. And then the tracing coverage and the tracing window, which describes how many days back from the detection of a case we trace their contact. And then if I have time, I will show some effects of, so what can a short-term interruption of contact tracing cause when the resources are limited. So as I said, we took parameters from COVID-19. This means that we fixed the generation time distribution, which describes the shape of the function beta of the infectiousness. And we fixed the incubation time, which is the probability of having symptoms at each time. And from the probability of having symptoms, we have obtained the probability of diagnosis by just saying that, okay, every individual is or some individuals, a fraction of individuals are diagnosed after a certain delay from symptoms. So, for example, after 1 day from symptoms or 2 days from symptoms. And one very simple analysis that one can do with having analytic formulas for the reproduction number is to understand what diagnosis or tracing efforts are needed to stop the spread of the infection. And this first plot is made with a reproduction number of 2.5, which is close, a bit low maybe, but close to the unconstrained reproduction number of COVID. And these curves denote so the epidemic is controlled if parameters lie below these curves. And what this diagram shows is that with a higher reproduction number, such the one for COVID, only very high efforts extremely high efforts in diagnosis and tracing allowed to stop the epidemic. This corner here corresponds to a very high fraction of contacts that are diagnosed, so symptomatic individuals that are isolated, and very short delays to diagnosis. And then the orange line corresponds to a contact tracing that finds all contacts, and yellow and green and so corresponds to less contacts found. So this shows that, this shows that we need high effort to control the epidemic. But then things change when we assume that some other measures are in place, and here is the same plot, but with a lower reproduction number. So this means that some measures like physical distancing or lockdown are already in place. Then we see that the region of parameters that allow to control the epidemic is much wider. So if we have managed to reduce transmission in the community, then we need it is easier to then bring the epidemic to control the epidemic. We have investigated, so briefly here, we have investigated the effect of tracing contacts for 2 days or 3 days or 4 days before the detection of a case. And here and this is the reproduction number that we obtain after tracing. And I just want to show the effect of that increasing this time and searching for more contacts as expected brings down the reproduction number. And in this figure, I just want to show why is contact tracing important? this plot here on the left shows the solution of the equation. So this H subscript C, so the tracing rate for different time windows, so 2 days, 3 days, 4 days, 5 days before detection. This is the profile of the solution we observe. And here on the right, I have put together the tracing rate with the diagnosis rate. So this means that without contact tracing, the probability of being diagnosed follows this profile, this lower profile here. But when we add contact tracing in the community, the effect is really to increase the probability of being detected in, in the x-axis here, I have the time since infection. So when I add contact tracing, the effect is really to increase the probability of being traced very early on in the infection. So really the effect is to stop and isolate the people as soon as possible after they have been infected. And this is the important effect of contact tracing. Now, maybe, if I have still 5 minutes, I will show this is a last test we have performed to show the importance of evaluating carefully when to stop contact tracing. So on the left here, I have plotted the epidemic in the sense that the blue line denotes the incidence, so the number of new cases every day. And the yellow and red lines denote the number of individuals that are diagnosed or traced. And on the right, I have plotted the computed growth rate. So the growth rate estimated from the incidence here to the left. And so for some reason, sometime it is necessary to stop contact tracing in a city or in a region because maybe resources or efforts have to be focused on a different city or a different region for which is in a worse stage of the epidemic. But the idea, what we wanted to show here is that this should be done very carefully, because if an epidemic was controlled with the contact tracing, so here we observe an epidemic that is initially decreasing, and then at some point we interrupt contact tracing for some reason, the growth rate here jumps high, jumps positive, and the epidemic starts to take off. Then this first row show an example when contact tracing is introduced again, because the epidemic was not too high, then the growth rate goes back to the original level, which is negative, and the epidemic declines again. But this is not always true if there's a limited capacity on tracing resources. So limited capacity means that if the incidence is too high, then we don't have enough people or resources to search all the contacts. So more individuals will escape tracing. And in the bottom panel, we have shown an example where the interruption of contact tracing is longer. And when contact tracing is resumed, this tracing capacity is exceeded, and the epidemic will never, and the growth rate will never go back to negative as it was before. It will always stay positive, and the epidemic will spread no matter contact tracing or not. So this was a qualitative example of the mechanisms that are behind contact tracing. And okay, so just to conclude, I want to stress again some of the strengths of the modeling approach. So the main strength of the modeling approach is that we have started from individual level processes, and then we have computed the population behavior. This means that every term has a precise interpretation in terms of individuals, and we can interpret population quantities with individual level quantities and go back and forth and interpret precisely every term. And ASIS infection structure allows to include realistic distributions of the infectiousness, for example, or the incubation period, and so on. The model is deterministic. This means that although there are some simplifying assumptions, but it is easy and fast to simulate. And this is convenient, especially when we need to repeat simulations many times. For instance, if we need to do parameter estimation. And the relations between model parameters and output are more transparent, so we can get general insight. There are some limitations due particularly to the deterministic nature of the model. The main limitation is that homogeneous mixing ignores any clustering, for instance, households or super spreading events, which are shown to be quite important in contact tracing. And I have assumed instantaneous contact tracing, but this is not actually a structural limitation because we could include delays in a realistic way. A more structural limitation is that I have assumed that the infectiousness of an individual is independent of the incubation time. And this is probably not true. They are probably related, and this should be included. And something that is, again, not structural, but important in practice is that this model accounts for the tracing of infected individuals. We have ignored the fact that contact tracing sometimes also finds healthy individuals, and they also have to quarantine sometimes. If we get a message from the app that says that we got in contact with some positive individual, we should still quarantine. And this is excluded in the model. So for practical purposes, this is quite important. And then what we are working right now is on extensions to different strategies like backward and full contact tracing. Now, something I haven't added here, but we're working on is more mathematical aspect of the model that I have ignored here, like we get a very interesting system of integral equations, and we need to work on the existence and uniqueness and mathematical properties of this model. But yeah, this is all what I wanted to say. So I thank you very much for the invitation, for the attention, and if anyone have question, I'm happy to go back to some concepts. Thanks a lot.
Thank you very much, Francesca, for your nice talk about this topic. So yeah, are there any questions, suggestions, or comments maybe? Barbara, maybe you? We don't hear you.
Yeah, no questions from me. I've actually heard the talk before, so.
Oh, okay.
But very nice talk, Francesca.
Yeah, I hope it was not too boring if it's the second time you hear it.
No.
Any other questions or suggestions maybe? Well, if not, thank you, Francesca, once again.
Thank you. It was nice to get an invitation from you.
Here in Koper, at least virtually. But hope you will have a chance to visit us in live when this.
Yes, I hope so too. Yeah, that would be nice. Thank you very much.
Thanks, Francesca. Sorry, Francesca, can we meet on Zoom briefly on my personal link now? Do you have some time?
Sure.
Yeah, okay.
Yeah, if you can send it again.
Yeah, I'll send it again.
Okay, thank you.
Okay, cheers.
Okay, thank you again, and see you.
Thank you. Have a good day.
Bye.
Bye.